Hello everyone. In this problem, there are two populations of an animal species P. Two populations satisfy Hardy-Weinberg equilibrium, and the size of one population is twice the size of the other. This animal's body color is determined by gene A, located in autosome. A allele is dominant over A asterisk allele. We need to determine these two genotypes out of these three. Using these three statements. For the first statement, at first, because A allele is dominant over A asterisk allele, that means A homozygote and heterozygote has a gray color, and A asterisk, a homozygote, has black color. So the number of individuals with a black body color in population 1, let's say the size of population is n, and for the black color, if the frequency of A asterisk allele is Q, to have a black color, it should be Q squared. And for this genotype, this one is not A asterisk homozygote. In such case, the ratio will be 1. So let's say the first genotype indicates a heterozygote. In such case, the number of individuals with the genotype is n times 2pq, and n cancel, q cancel, and if this is equal to 2/3, that means the ratio of p and q is 1 to 3. And because the sum of p and q is 1, that means the early frequency of p is 1/4, and early frequency of q is 3/4. And for the second statement, because this ratio is less than 1/2, it is likely that the second genotype is A asterisk homozygote. We need to exclude this genotype to make this frequency less than half. So without A asterisk homozygote, A homozygote is p squared and heterozygote frequency is 2pq. And from this homozygote, half of their genes alleles are made of A asterisk. So for the numerator's frequency is pq. So cancel p's from numerator and denominator. And because p plus q is equal to 1, that makes 1 plus q in the denominator. And because q is 3/4, that's equal to 3/7. So that means the second genotype is really the A asterisk homozygote. And for the third statement, this value is close to 1/2. So it is likely that the second population's size is twice the size of the first population. So let's assume that the second population size is 2n, and a second population has different allele frequency. So for the A asterisk homozygote in the second population, the population frequency will be q prime squared. And the heterozygote for the first population frequency is 2 times pq. So cancel q and n, and p is 1/4, q is 3/4, and then 1/q prime squared. That's equal to 25/48. So I simplify the denominators. That means q prime squared is equal to 9/25. So q prime is 3/5 and p prime is 2/5 in the second population. So if we choose the right statement from the box, the first statement is true. In population 1, the allele frequency of A allele is 1/4. And for the second statement, in population 2, the number of individuals with black body color is 2n times q prime squared. And in the first population, the number of allele, A asterisk allele, is n times 2 times q squared, because we are counting the number of allele. If the it's a homozygote, we are going to multiply 2 because there are 2 alleles. And for the heterozygote frequency is 2pq, and in this case we don't have to multiply 2 because each individual has 1 allele. So cancel 2 and n. And the denominator is q, because p plus q is equal to 0. And numerator is q prime squared. So q prime squared is 9 over 25, and 1 q is 3/4, so 4 over 3 for the reciprocal. So the ratio is 12 over 25, not 3 over 25. So second statement is false. And for the third statement, if we look at population 2, female is heterozygote, and she is going to mate with male randomly within the population, and we want to find the probability for the offspring to have a gray color. So for the male, there are 3 genotypes. And in population 2, each frequency is for the A homozygote, that's 4 over 25. For the heterozygote, that's 12 over 25. And for the A asterisk homozygote, that's 9 over 25. And if the heterozygote female have offspring with the first genotype, all of the offspring will have a gray color, so the probability is 1. And if both of the parents are heterozygote, the probability of gray color is 3/4. And a heterozygote with A asterisk homozygote, the probability for gray color is 1/2. So multiply this frequency and probability for each case. And add them all. So the first probability is 4 over 25. Second case is 9 over 25. Third case is 9 over 50. So if we add the first two fractions, that's 13 over 25, which is 26 over 50, and adding 9/15, the sum is 35 over 50, which is equal to 7/10. So the third statement is true. So the right answer is the fourth choice. That's it for this video, and thanks for watching.